All right, I wanted to now look at some of the more Physics 208C oriented applications of our more conceptual look at general relativity that you saw in the last video. And one of the first things that I want to look at is the formation of a black hole. What do we say about this? Well, we said that it essentially has, quote, zero size. And so this could have the mass of our sun, or many times, in general, the mass of the sun. Smashed into a small volume. Now, how can we justify this? Well, as a mass, say this is an iron core of a star that's crushing down. As this iron core gets smaller, you can say, well, according to Newton's inverse square law, the force goes as 1 over the distance squared. So what that tells us then is as it gets smaller, the force vectors start out like this. I'll just draw them a little smaller here so I can make them bigger here. As the thing gets smaller, the force is going to go up. So if this is R, this is R over 2, then this force F2 would be 4 times F1. Or that would be the F1. So a typical force then, if the particles on the average are twice as close together, would result in a force that's 4 times bigger. So then you can continue that process. You say, well, that force keeps going up as the square of the distance. And eventually then, by the time that in the limit, as r goes to 0, the force approaches infinity. And so that would then tell us that there's no known force in the universe that can stop the collapse. And how can something be smashed down into essentially nothing, to 0 volume? You say, well, because there's no known force in the universe that can stop it. If nothing can stop it, you're forced to the inescapable conclusion that it smashes to 0 size. Or at least so small that size doesn't have any meaning anymore. Okay, that may not necessarily be the same thing as 0, but small enough so that it would be impossible for us to measure how big it was. It would be on the order of maybe the Planck length. So that's what we think the minimum possible size might be. Which would be an astonishingly small number, something like 10 to the minus 35 meters, or 10 to the minus 35 centimeters. But when we get to that point, distances stop having meaning. Okay, and so how would this work? Well, you could imagine space and time on the order of, let's say, 10 to the minus 32 meters. Then space and time has a little bit of fluctuation, even in a vacuum. Okay, and why is this? Well, because delta E, delta T, even for the vacuum, is approximately equal to h bar. And so we start getting little blips of energy that come up, that arise in this sea of nothingness, basically borrowing energy from nothing, as long as we can pay it back fast enough. Okay? And another equivalent expression is delta P delta X, approximately equal to h bar. So we could say that over small time intervals, these blips come. We could also say over small spatial extent, we have a fluctuation momentum. That fluctuation momentum will also curve the space. Okay, because that has an energy content to it. That goes something like delta E is something like delta P squared over 2m. Non-relativistic kind of an expression. Okay, so what this is showing us then is that at smaller times and smaller distances, the structure of space is starting to become more distorted. And so if we go down to, say, 10 to the minus 34 meters, now the change in the distance is much smaller, only 1/100th of what it was for 10 to the minus 32. That means that the fluctuations in momentum, this is like what could cause virtual particles, for example. Everything starts getting bumpy. It's like you look at an ocean wave, it looks pretty smooth on a large scale, but if the wind is blowing, you look in close, you can see that it's actually kind of choppy. Okay, and that's what happens at 10 to the minus 34. But when we get to 10 to the minus 35, the very structure, a fabric of space, becomes extremely irregular. And so you have some places then where you could have huge fluctuations, so great that you could produce a black hole just in that very small area, just due to the fluctuations in the space. But you can't really get any smaller than that, because if you did, then the fluctuations in time would be so small, fluctuations in space would be so small, that the energy content would be so much that space and time would just be completely turned inside out, back around on itself. And so this is thought to be the limit then of distance is the Planck length. And so at that length then, it's not that distance is 0, but how do we measure distance? We measure distance by measuring between 2 points, what the length is. So if we look at it at one moment, then we look at it at the next moment, and the topography is changing, then this is point A and this is point B, and the length is different between A and B. Same 2 points, but now the space has been, because it's constantly fluctuating and so energetic, the length AB is poorly defined. And so when we get to that point where the curvatures become so great that distances are no longer well defined, and the uncertainty in the distance becomes bigger than any structure could be in that location, then we say that size stops having meaning. Okay? And so that's why we think that the minimum possible size is somewhere on the order of the Planck length. And so that's how small these black holes could get. So how small is this? Well, it's as much smaller than a bacterium as a bacterium is smaller than our galaxy. And so we're actually closer to being the biggest thing in the universe in terms of powers of 10 than we are to the Planck length. We're much closer, as a matter of fact, to being the biggest thing in the universe if we multiply powers of 10 bigger than if we tried to cut powers of 10 smaller to get down to the Planck length. We're closer to being the biggest thing in the universe than to the Planck length. Okay, so that's what we mean then when we say it's been smashed to 0 size. Not necessarily 0, but way smaller than the head of a pin, way smaller than an atom would be. And we're not exactly sure what this limit is, but we think it may have something to do with a dimensionless constant that is associated with what we call the Planck length. And I'll talk more about dimensionless constants and how this particular one has units of length. But Planck came up with that. And he did it by finding combinations of constants like g and h bar and the speed of light that when multiplied together had no units, or had units of length in this case. And those would be natural units of length, because it wouldn't matter what coordinate system you looked at, they would still be the same because they don't have any units except for the units of the quantity being measured. So there's such things as a Planck volume, a Planck mass, and those kinds of things we'll look at later. Okay, So we just established the fact that the object will smash down essentially to zero size, but not quite to zero. The problem with doing this with Newtonian mechanics is that this is not quite right in general relativity. The inverse square law works pretty well for big distances, and so we use it then to figure out our trajectory of our rockets that go to Mars. And so that works fine there. But if we start trying to figure out what's happening around a black hole, we end up with deviations. That's where Einstein's general relativity theory starts to break down a little bit. It's when we get to these really small distances. And the Newtonian gravity is even worse. Okay, but up to a certain point, Einstein's general relativity is more accurate. So a more accurate description up to a certain point at least, for the formation of a black hole uses curved space and time. And E equals mc squared. So let's imagine then that we've got two masses. Just for the moment, we'll look at the interactions between two masses. And instead of using the inverse square law, we're going to use this more accurate approach that uses curved space-time and E equals mc squared. So as the two particles start to feel an attraction, you can think of the force that is preventing them from coming closer together as being like a coiled spring. Okay, because eventually you get these atoms close enough and the electrostatic force will become very large. In the case of a nuclear field, even nuclear forces can be repulsive. But the force of gravity is forcing them closer together. And so as they start to move closer together, say from point A to point B, where now they're closer together, like this, now there's more potential energy. Now it's not really a spring that's storing that energy here, but rather it's the repulsive influences of the fields that are pushing apart. Say if this is two electrons being crushed together, or a proton and a proton being crushed together, there's going to be a tendency for them to want to fly apart, but gravity is dominating at this point. So there's more potential energy, but because E equals mc squared, that tells us that with more potential energy, there's more mass. But more mass means more gravity, which is more curved space-time. So more energy curves space-time more. And so that creates more gravity. So instead of thinking of it as being a bigger object going to a smaller one and having the force automatically go up by a factor of 4 by an inverse square law, we have to look at a series of these perturbations that are caused by general relativity, where the masses get closer and closer together. Associated with that higher state of potential energy, there's more mass, more curved space-time, more gravity. So then that brings us to point C. Now they're really close together, like this. And so that's more potential energy. E equals mc squared. So that means more mass. More effective mass as the objects get closer together. That means more gravity. And so if we continue this process mathematically, we find the process is unstable and it will continue to smash down until the object reaches the size of a black hole. it just keeps creating more mass, which creates more gravity, which creates more compression, which creates more potential energy, which creates more mass, creates more gravity, and it's a downward spiral to the formation of the black hole. Okay, so that is the first point I wanted to discuss. The next one is, we said before that a black hole essentially has a singularity at the center and an event horizon. Here. Okay? But when an object falls through the black hole and decides to explore the interior, at this point, past the event horizon, space curves back on itself. Okay, and so that means then that if you're moving in a rocket ship, the space that you're moving through is actually curved back on itself, and so that means that you could see the back of your own head. So you could comb your hair without using a mirror. Wouldn't that be awesome? That would be really cool. But it shows that that's why you can't escape. The rocket, even with an infinite amount of energy, is going through a geometry of space that's curved back on itself once you go beyond the event horizon. So if we plot space and time near a black hole, what we find is that if this direction here is space, and this direction is time, we saw before that time stretches near the singularity of a black hole. And so essentially this is like a hole that has zero width and infinite depth. That's what we're talking about when we form a black hole using the principles of general relativity. And also recall that as the rocket approaches the event horizon, more and more time is going to elapse if they're viewing the Earth. And so this is 1 second near the event horizon. Whereas this might be 1 second on the Earth, which is far away from the strong gravitational field of the black hole. And so this is why then you would see many seconds elapsing on Earth's clock, while only 1 second elapses on your clock. So if you're close enough to this event horizon, you could see the Earth going around the sun 100 times a second, but the Earth looking at you through a closed circuit TV monitoring camera would see you essentially as being frozen, and maybe 1 second on your clock would go off every 1,000 Earth years or something. And so that is the effect then that a black hole has on space and time. And so you would think, and a lot of this is just kind of a review of what I talked about in the previous videos, but I wanted to mention it again for clarity and also so that it's fresh in your mind when I talk about this next subject, and that's Hawking radiation. There actually are ways for particles to escape from a black hole. So eventually then, this is a quantum mechanical effect, not a classical effect. So Einstein's general theory does not predict this. But Stephen Hawking was able to show that this was true because of quantum mechanics. So basically then, particles do escape from a black hole. And here is the mechanism, although it's somewhat watered down from Stephen Hawking's actual paper that he wrote on this. But let's say that this is the event horizon. And here we have a particle and another particle forming near the event horizon. We'll call this a virtual particle pair. Okay, so this virtual particle pair then can form anywhere in space, but it turns out that if the virtual particle pair forms near the event horizon, one of these particles can tunnel through the barrier. And so this particle escapes. Before it has to pay back the energy. So remember, the virtual particle had zero total energy, right, to begin with, but it had to borrow this energy to create this virtual pair from the uncertainty principle. And so this particle escapes by means of quantum mechanical tunneling, which we've talked about before. This is another application of quantum mechanical tunneling. Tunnels through the barrier, even though the barrier is too high for it to escape with classical means. And it would also have to move faster than the speed of light to do this, because we saw that at the event horizon, the escape velocity is the speed of light. So it's violating every principle in the book. Remember, the uncertainty principle trumps all these other relationships, like conservation of energy, conservation of momentum, speed of light barrier. They're all secondary to the uncertainty principle. So the uncertainty principle allows then for the particle to escape by quantum mechanical tunneling before it can recombine. And so it gains positive energy. It acquires, we should say, because of its increase in potential energy, it has acquired positive energy. Let's say it's gained positive energy. But the only way to conserve energy then is to have the pair now has negative energy. Because now they can't recombine. So the only way to pay back the debt is to give this particle negative energy. And so it's like, you know, let's say that, I don't know, you go to the bank with your friend and you borrow this money, but then you have to pay it back. And so your friend takes off with all the money. And so then that means you've got to pay it all back. So you've got this negative deficit of money because you're in debt now, and left you holding the bag. So now you have to you acquire negative energy. Now, does this mean antimatter? No, not necessarily. What this means instead is negative mass. That's like anti-gravity mass. Negative mass would actually repel normal positive mass. Okay, and so that's the kind of thing that we think is necessary to create certain shapes, for example, in wormholes, for that we discussed earlier, if in fact they can be produced. So we need negative energy, and this negative energy may in fact have something to do with how the universe is flying apart due to dark energy. There's a repulsion force called dark energy that nobody quite knows what's going on with it, but it seems to be produced out of empty space. and seems to be repulsive too. So it's like an anti-gravity effect. So this is an anti-gravity effect. And so this negative particle then falls toward the singularity and cancels out some of the positive mass in the singularity. Because negative and positive will cancel out. Okay, so the negative mass and the positive mass of the singularity cancels out some mass. And so the black hole then shrinks a little in size. So the event horizon shrinks. Why? Because the event horizon is proportional to the amount of mass in the black hole. And the mass in the black hole has decreased. So where did this mass go? Well, it went into the Hawking radiation, which is produced by this bizarre virtual particle effect and tunneling that happens. And to conserve energy, the virtual particles must fall toward the singularity and cancel out the positive mass that's in the singularity. So the net result of all of this is that the black hole evaporates off mass and shrinks. So over time then, we think that eventually the universe will just be comprised pretty much of black holes, in the far, far future. But then finally those black holes will evaporate over even longer periods of time. We're talking about googly years, 10 to the 100-year types of times. Over that period of time, all of the black holes in the universe will eventually, all the matter will eventually form into black holes, we believe, because that's the highest entropy state for mass, is to turn into a black hole. And entropy is constantly increasing till the whole universe is made out of a bunch of these black holes. But then the black holes evaporate over incredibly long eons worth of time. Now, has this been proven yet? Not exactly. Or Stephen Hawking would have gotten a Nobel Prize while he was alive. But there are a lot of details of this that people are taking very seriously. And it appears to be true using analogs of black holes. So they have like sonic black holes in which the properties of these sonic black holes are supposed to be mathematically very similar to real black holes that give rise to something that's analogous to Hawking radiation. And so we do in fact believe that this sort of thing is happening in the universe. To actually be able to prove it, we would need to find one of these black holes actually evaporating. And how could we find that? Well, it turns out that in the last little bit, when the black hole has evaporated down to a small size, you get many black holes. Eventually. After maybe 10 to the 100 years or so. Enormous lengths of time, depending on the original size of the black hole. You eventually get down to these mini black holes. But do we have mini black holes right now? We might. Okay, so even though the only black holes we know about now are really big ones, there's evidence that we may have smaller black holes that are actually orbiting in our own galaxy. And so it's possible that these are around right now. But the ones that we've been able to determine are black holes aren't going to get to this state for a very, very long time from now. But let's just assume that there were some mini black holes in the universe today. Then the energy barrier for the particle tunneling is smaller because it doesn't have to escape from this highly curved region of space-time. It doesn't have to overcome such a big energy barrier. And so we think then that these mini black holes will start to accelerate their evaporation. Until eventually it's accelerated so much that it finally explodes at the end. The evaporation is so rapid that it looks like an explosion. And so that's what's predicted, and that's what we're looking for. If we can find little mini black holes that are exploding, and if many black holes were made, say, right at the Big Bang, then there could be, according to some calculations, some of them that are just ready to pop off right now. And that it would have a certain characteristic signature, and that has not yet been found in observations. And so that's why Hawking didn't get his Nobel Prize.